Hello and welcome to binarysearch.com. Today we have training on bit manipulations and things like that. So for those of you who don't know, binarysearch.com is a platform to prepare for interviews and also to learn algorithms together. And it's pretty important. Like on most other platforms, you will have just problem sets, right? And maybe some kind of discuss forum with editorials and stuff like that. On binary search, however, if you head on to practice, you can create a room and you can basically practice algorithms with your friends. If you have friends on that platform, you can create a room, invite them, and you'll be able to solve problems online together. And also you can solve problems with random people. So if you just create a public room, everybody will see this room. They will see some parameters like what are the topics selected, what are the difficulties. They will be able to join and you'll learn potentially from random people. I mean, I'm constantly solving problems here. I joined, I think like 2 weeks ago, and I already solved like over 200 problems, most of them in public rooms. So yeah, you can chat with me there when I'm solving problems. Maybe I'll comment on your solutions. It's not like the main way. It won't be the intended way of our communication. But if you ever come to that platform and see me solving problems in a room, you can definitely join and ask whatever questions you have. So yeah, if you come across me on that platform, definitely join my room. We'll practice some algorithms together. But today we're not going into public room because I want to discuss like very specific topic. I can't set up a room with that topic, but it just won't be as simple as just checking this problem straight away. Let me immediately open a bunch of them. We'll cover most of these problems. Except for that problem, we won't go into details. And for that problem, we'll cover only C++ implementation. So for all other problems, I have a solution in C++, I have a solution in Python, so whatever works best for you, you'll be able to check it out later on GitHub. And of course, I'll put links to problem sets and my solutions down in the description. So first problem asks about how many set bits there are in all numbers from 1 to n inclusive. And the main difficulty is that it has to be done like pretty quickly in logarithmic time. So actually, yeah, first of all, we'll do something like that. So it is not particularly difficult to compute number of set bits in like one number, right? You can just write a short loop. You can use something like built-in pop count, something like that, right? But here you have to compute number of set bits in all integers from 1 to n. And actually this constraint, it's a hint. Because like when something can be done in logarithmic time, it usually means that you have some sort of recursion, which decreases the size of arguments in 2. So we not only have bit manipulation, but we often see like bit manipulation combined with something. Here, for example, it's recursion. And that's exactly what we do. Like if you write down the answers for several first numbers, like up to 15, there is a high probability that you'll figure out what is the recursion. One way to do it is it is natural to partition all numbers into even and odd numbers. Whenever you see like bit manipulation problem, definitely try to think about like, does it help to consider whether the number is even or odd? And if you look at the binary representation of all these numbers, what will you see? We'll see that all of them have last bit of 0. That's what it means to be even, right? And if you remove it, you effectively divide number in 2. And you get numbers like 1, 2, 3, 4. And you immediately recognize like, this is a recursive call. So if you want to compute number of side bits from 2 to 8 in even integers only, and you can just make a recursive call. So in this case, we need this recursive call, right? If you look, however, on these numbers, you'll find out that all of them have last bits of 1, right? That's what it means to be odd. So we have like some numbers here, 4. All of them have 1 bit at the very end. And when you remove that bit, what you get is like 0, 1, 2, 3, etc. And it's another recursive call. So you need 2 recursive calls, and for odd integers, you discarded 1 bit from each of them. So you add some additive constant as well. Now, depending on whether we have whether n is even or odd itself, we have some details. Like for 7, we have 2 recursive calls to different things. For 9, we'll have recursive call to 4, so twice the same thing. But it's like the implementation details. So yeah. If you just implement recursion like that with recursive calls, then you will say like, wait a second, like, okay, we do 2 recursive calls, but they and reduce the size of the problem in 2, right? If you know like some master theorem or whatever it is called for solving recurrences, and you say like, this takes a linear time. Correct. If implemented like just return this, it will work in linear time. But the cool thing about these kind of problems is, yeah, let's take a look. Like we make a recursive call from 7 and 8, and get to 4 and 3. And make a recursive call from 4 and 3 will go into 2 and 1. Right? So, actually from 8 we also call 3, from 4 we call 1. And the point is that on every layer of our recursive descent, we have only 2 numbers. If you consider like, suppose like currently we are interested in values and answers for 2k and 2k minus 1. What queries will you make? Like for this, you will get into k and k minus 1. And for this odd, you will get just k minus 1. So you had 2 numbers, you will have 2 numbers in the next layer. And the way to not to think about like how to do it efficiently, you just create an ordered map of hashed answers, or cached answers, I should say. If you don't know the answer, if the cache does not know the answer, you add it to cache first, and you then always return like from cache. It's like 100% working method to speed up your recursion. We had a problem at 8coder, actually. If you're watching like more of my editorials, and you may notice that not that long ago, we had a last problem of 8coder beginner contest. It was also something about this recursion with caching, with answer caching. It's very useful. So it's pretty hard otherwise. So yeah, this is an idea that I wanted you to learn from that problem. And when you just start out with bitwise manipulations, and you want to check that some number is even, you can just take mod 2, right? No big deal. No, another possible option is you can write like this, and it's considered, I believe, a more professional way to do it. And it checks that n is odd. So here you will have like n is even, right? What it does, it takes a bitwise AND with number 1. Number 1 has a lot of zeros at the beginning and a single one set. And all the zeros, they discard all bits of n except the last one. So this effectively equals to the last bit of n. If last bit is set, it means the number is odd, right? Because all numbers or all bits starting from second, they correspond to powers of 2 and are even, right? So 2, 4, 8, 16, 32, whatever. They are all even integers, and it's the only last bit who determines whether the whole number is odd or not. It's considered a more professional way, but I decided like when we are only starting with this thing, I'll just do it explicitly. More or less the same thing happens in Python. The only inconvenience is that for whatever reason we have this solution class. We have to go to self. Not particularly nice, but whatever. I mean, it's the same thing. Dictionaries, I think, yeah, like this is an ordered map in Python. If you want to ordered map, then I believe. Actually, I'm not sure. I'm not sure what ordered dict does. So let's not talk about it. Now another problem. It's easier. It asks you to check whether the given integer is the power of 2. Now, obviously, you can again do it recursively. 0 is not a power of 2. 1 is a power of 2. All odd integers that are not 1 are not powers of 2. And if n is even, you can just make a recursive call. It's possible. There's also one much shorter solution that I would like to show you. I believe you can do something like that. Right. Right, it's also a possible way. Now, there are a couple of different built-in functions that work with bits. Again, like if I'm saying this third time this week, but since C++ 20, there will be a standard header named bit, and there will be a lot of functions, like all of these things, they will be there. In particular, built-in count tail zeros, or tailing, or whatever they call it. So it is a very fast way to check what is the maximum power of 2 that divides n. Okay. How many tailing zeros number n has? Well, if you know some basic numbers here, you may know that every number you can like factor out whatever is the max power of 2, and then you'll remain with some odd integer. Right? And basically, like built-in count tailing zeros, it returns k. So however many zeros there are at the end of n, it's the power of 2 that n is divisible by. So it returns this, and then this binary manipulation, it says like take 1 and shift it that many to the left. Now, every time you shift number to the left, it's the same thing as multiplying by 2, right? An interesting thing happens when you shift like by k. It's multiplying by 2k times, so that's it, multiplying by k by 2 to the power of k. That's another possible way to check whether a number is power of 2. So this expression returns 2 to the k, and you effectively check that m is equal to 1. But it's a kind of cheating way. Like, maybe it's not. I'm not sure what is the expected solution for this. Is that some cheating solution? I don't know. Like you can find some very specific pattern to that. Well, I believe it means that they turn like subtract 1 and check whether like is any bit that has not changed. Well, possible. So another possible option is that get number of set bits and check whether it's 1 or not. But I believe it won't work for negative. I'm not sure whether or not like built-in pop count works correctly for negative integers, because you may know that like there's a leading bit does not represent a power of 2, it represents sign instead. We have many different solutions. All of them are fine. The way I would probably do that in the contest is built-in. If I want to teach recursion, then I will do that. I'm not exactly a big fan of like noticing some patterns, because in contest, like if you notice a pattern, it may be like almost correct, but it's off in one case, and you have to add another if, make a resubmit, lose 50 points or whatever the penalties and cost forces. Like, unless you are 100% sure in a pattern, I doubt it. Recursion also requires some base cases, but they're rather straightforward usually. built-in, if you're confident that your input is not malicious, so it's like it must 1 billion, then or something like that. I mean, it's usually what happens in contests, or at most like 10 to the power of 18. Then you just want to take 60 bits, right, instead of sorting. Then built-in functions work perfectly fine. They are fastest of all. In some cases, it's also important to make some bit manipulations in constant time. And it's exactly like, for example, in our recent lecture about lowest common ancestor, we wanted to compute what is max power of 2 that fits between left and right, and we absolutely needed to do it in constant time. Like writing a while loop there was not an option. And it also overlaps with the topic of today's short modern video. If you haven't watched it, so you're welcome to watch. Just a very short video when I present a couple of thoughts about CodeChef editorials. Yeah, so this works perfectly fine. In Python, you can just translate it the same way. Like, recursion is totally fine. If you don't want to think about bits itself, and then in some simple problems, you can get away without like any bitwise operations. Let's check the next problem. Number of set bits, again, you obviously can use built-in pop count. You can also do it in the same, like with a while loop. You can do it with recursion. This condition checks that number is odd. You obviously again can do it like that. I mean, like, sometimes you have to write code like this. Sometimes I write it just because it's faster to type. It's perfectly fine if you want to think about even and odd integers in this way, just a little bit slower. Also, when you want to remove last bit, you can shift 1 to the right. It will discard the last bit. But you can also explicitly divide by 2. I mean, this is a problem. Just the correct way to count bits is from smaller bits to larger ones. Yeah, I mean, if you were to write it the other way around, then it would take log squared time. So yeah, again, like if you don't want to think about bits right like that, in terms of even and odd integers, if you want to think in bits, then something like this is your way to go. You can also make it a recursive program, but I just wanted to show like what are all possible techniques for these problems. And again, you can just return underscore built-in underscore pop count. In Python, it's the same thing, so that's not shy. Longest consecutive run of ones in binary. It's a bit more interesting, but it's more or less the same thing. So all of these problems, like what is the longest consecutive something, you just maintain what is the current run, what is the longest run. You iterate effectively over bits. You will remove bits one by one, and you check like whether if the current last bit is set, then your current run increases. If it's off, then your current run ends, and before you end it, you want to take max for longest run. If current run is bigger than longest run, then longest run will update. Also, at the very end, if you don't want to think about like, oh, what happened if my current run has not hit that condition, but instead hit this condition, right? It's possible. Like for numbers like 4, your longest run will be at the very end, and it won't hit this condition. A way to not to think about it and be like very confident, you can just take another max at the end, right? It won't harm. It won't hurt you. Longest run can get the current value of current run at any point, because current run is always a correct, a valid length of run. So you can, if you're not sure, you can write this statement how many times you want. I sometimes just spam it like in every branch. If I'm with my more involved problem on the same topic does not work straight away, I may just spam it in several different places, because I'm always sure that current run is a valid run. So I can always do this. And if I'm not sure when it's necessary, I mean, it's no harm to make it when it's unnecessary. It's a little bit slower, but usually in such problems, you're not having any issues with speed. Right, so in Python, it's the same thing. For this first easy and medium problems, I just wanted to do whatever is the most clear solution to explain. And I think that in interviews, it's important. Explaining your solutions clearly is very important. And sometimes it makes more sense to implement a simpler solution that is easier to explain than some cheating with built-in pop count. Right? So yeah. Between two solutions, one is like hard to explain and one is easier to explain but a little bit less efficient, I would usually choose one that it's easier to explain. I mean, complexity is the same, you agree with me, but probably you have more necessary operations, or just check whether a number is odd in this way instead of checking with bitwise AND with one. But here again, you can do like this, you can do like this. Whatever you're more comfortable with. I suggest, like, if you're not 100% comfortable, I suggest starting like this. And once you feel like you can understand what these guys are doing, then switch to this, because it's just better. Okay. Or actually, I'm surprised. Yes, okay. So here we want to compute Hammond distance. You can do it very explicitly. Of course, you can. I'll show like what is the intended solution in a second. But you can compute it explicitly. So you just create a counter. Whenever the last bits of your arguments are different, of different parity, it means that last bits are different, you increment the distance, and you remove last bits. So this pattern stays the same. You check modulo 2. You can also obviously write like bitwise AND with 1 here, and you can use shifts here. And you can do the same thing in Python. Intended solution, I believe, is when we take built-in pop count of x XOR, where is, okay, x XOR y. And the way it works, XOR is an operation that we have not seen yet, and it's very important on bitwise problems because of the following reason. It has several nice properties. In particular, you want to count number of different bits, right? And you have something like that. These bits are different, these are not, these are not, these are different, these are, this are not. Yeah. So the answer will be 2 here, right? Now what XOR does, is it returns exactly that, whether bits are different or not. If bits are different, then it's 1. If bits are equal, then it's 0. So you first take XOR. Each bit represents whether digits are whether bits are different or not, and then you can just count number of set bits in this number. So it's useful to know all of these built-ins, and also that you can just XOR numbers sometimes. And in Python, you can also I'm not sure about built-in and things like pop count. No, actually. Yeah, I'm talking too much recently. So, yeah. You can take XOR, you can get binary representation. It will be a string and you can count number of ones. I don't know whether it's like a built-in function that returns number of set bits straight away, but this is like one possible way to do it. It's not much, it's shorter actually than C++. And just keep in mind, like, get familiar with these functions. Once you got familiar with them, you can definitely use them. They save some time. Okay, count leading zeros is important for taking logarithm. Count tailing zeros is important when you want to discard like a couple of last bits that are 0. Pop count is important if you want to count number of bits. There are also methods like count leading ones, count tailing ones, but they are not as important in my practice. Oh, this is an interesting problem. We have next binary permutation. And for that problem, I copied my solution to count set bits count just to show that it works. Right, so, and it's also an important topic. Like, if you write functions and classes, data structures that you can copy paste into a completely unknown context, and they will work as intended, it's a good sign that you can add something like that to your library. Now, obviously, you don't want to add set bits count to your library because it's already built in pop count, but it's just for educational purposes I'm showing this. So next binary permutation, you want like permute bits and increase number. And the way to do it, you can find whatever is the first set bit of the integer. And the way to check whether the bit at index I is set or not is you can take this one that we used to check against the lowest bit. You can shift it I bits to the left, and then you can check. When you take bitwise AND with number that has only one set bit, you get whether the same bit is set in the other number. No, obviously it's unnecessary. Another way to do it is built in. It's like this. And here you can use built-in pop count. But again, if you're not yet familiar with all these built-ins in C++, then you can just do it with a for loop. But it's not what I would like to see you doing. I would love to see you doing using built-ins and things like that. And but when you're only starting out with things like that, it may be better to write this for loop a couple of times before you fully understand what it's doing. Then you can start the built-ins and switch to using them. And what happens next is like when it's impossible to increase your number when unless we change this lowest set bit. So we immediately change it, and by adding this to n, like we make sure that we change the entire run of ones, and in this part we simply adding back ones that we removed. Like when doing so, we potentially decrease number of set ones, set bits, and want to add them back, and just wait to add the smallest possible number of bits back. But yeah, something like this. In Python, more or less the same thing. I believe I just translated what I wrote in C++. Oh, this is interesting. We have two-dimensional integer matrix containing zeros and ones. For each row and column, we can flip them all at once, right? And we want to, like, each row of the matrix corresponds to some number, and we want to maximize the sum of the results. Well, we have some examples here. Well, this is not a good example. I'll make my own example. Again, we have such matrix, like first row corresponds to 14, second row is 5, and last number is 9. We can flip the entire row or the entire column. Now, this kind of problems about flipping things in the matrix, they have very interesting interpretations that you have some sort of tableau. So a board of light bulbs, and you switch all the light bulbs on or off in the same column or row, or I should say like flip all the light bulbs to the different state. And it also has some connection to linear algebra, modular tool. I won't get into like hardcore mathematics details, but you may notice yourself, if you change all rows, all columns, I should say, and then you change all rows, then you end up with the same configuration, because each number got changed twice, which is the same as not changing at all. It means that in such problems, our operations are redundant. You can get rid of one of them. So they were not forming a basis of this vector space, which represents all possible states of the matrix. It was, in case you are interested, it was a 2 number of rows times number of columns. And these operations were redundant. They were not linearly independent. Now they are, I believe. And you notice that you want to maximize the sum. And if you have like leading 0, it's already not maximal. Because if you change like every bit, even if you had like 0 and then all ones, right? When you change, you get 1 and all zeros, and it seems like you got fewer number of ones, right? Fewer ones, whatever. I'll figure out this English detail later. This number is still bigger despite having much smaller number of ones, right? So this is also an interesting thing in bit manipulations. So like leading bit decides everything. It's the most important. So that's why we want to flip every row which starts with 0. So what, and we don't want to flip actually all other rows. I believe it gets something like that. And then we don't want to flip all other rows because we will just decrease our numbers, no matter what happens with these columns. And then in each column, they are kind of independent. So here you see 2 zeros, it makes sense to flip. Because after you flip, you will have, actually, I forgot what was here. Yeah, because after you flip, you will get 2 ones, which is clearly better. In the next column, you don't want to flip because there are already more ones than zeros. And this column you want to flip. So you get something like that. And that's exactly what happens in the code. So we iterate over rows to the matrix. The way to do it in C++ is you take auto-reference because you want to change rows. If the first bit, leading bit is off, then you want to flip the entire row, and the way to do it is you iterate again with auto-reference over the row, and you take XOR with 1. XOR with 1 is flipping last bit. Actually, wait. Yes, it's flipping the last bit, but here we have like the only bit, so it's essentially like it's flipping the bit. We can also write like column equals not column or column equals 1 minus column, but this is the most clear way to flip bits by taking XOR. Then you just compute for each column, what is the current sum, like whether it's optimal or not. And if you want to flip, if you flip, then you will get a number of rows minus current number of ones. If you don't flip, you get just current number of ones. That's you add whatever is best to the answer. And in Python, there's one very nice implementation detail, and it's zip star matrix. It's a very ingenious way to iterate over columns of a matrix. It obviously uses a lot of memory because I believe it generates the entire thing. So you get like twice as high memory usage, but it's just so much shorter. And I actually learned it when practicing in a room on this resource. So I don't write quite often in Python, right? So I didn't know about this trick, and just very cool. I'm still on. It still seems like magic. But what it does, like when you unpack the matrix, you get rows. When you zip, you get first elements and second elements, and you get columns. It's just a little bit too smart. Yeah, I guess. I guess in next videos I'll try to talk a little bit less, and it will be like more like contest like solve stat because yeah, I have to save my voice a little bit. Right, so if you write in Python, definitely make use of it. It's just really cool. Okay. Another problem, let me just quickly check. Okay, we don't have all that many problems left. Okay. Long integer, we have list of numbers. We want to find all integers occur 3 times, except one that occurs only once. We want to return it, and we also want to solve constant space, although it's like it's debatable whether the space is actually constant or not. What we do, we want to count how many times each bit is set or is off. So the way to count like whether bit is set or not is again to take bitwise AND with one shifted that many bits to the left, and you just increment bit frequency. Then because every number occurs 3 times except one special number, like you can take frequency modulo 3 if our unique number has a set bit, and remainder will be modulo 3 will be 1. If it does not, then it will be 0. And here I can write like that, plus equal, but I also can write like that. And basically means or equals sets the bit, whether it was off or on. So if you don't want to worry about like setting a bit twice by plus equals, I mean, when you plus equal, you may accidentally set bit twice and it will change number. It will go to the next bit, right? If you don't want to do this, you can always make use of or equals. It will set exactly one bit, no matter whether it was already set or not. So in Python, we have the same thing. Yes. Actually, like this for loop can be replaced. So let's do it. One obvious way to do it is like this. Another way to do it is like this. So this is either 1 or 3 or 0. If it's 0, we like do not. If it's 1, then we get exactly what we want. So yeah, that's another possible way. Make use of sum function that can sum any range. In C++, you of course have accumulate. Actually, but for accumulate, you have to generate the range explicitly, I believe. And here you can make use of generator or iterator. Bit sum, another problem. Actually, what we wanted to. Oh, we have several numbers. We want to set a bit, turn the bit on k times. We can do it in any integer. Now, obviously, we want to increment the total sum as little as possible, by as little as possible. Obviously, the way to do this is to turn on the least significant bits first. And because we don't want to like iterate over all numbers, we are interested instead of like bit frequencies. Again, the same concept. In how many numbers the bit is set. And then we iterate from lowest bits to most significant bits. We check how many off bits there are. And we would like to turn these bits on first, right? And this is just an implementation detail that you don't want to turn more than necessary. That's why you take the max that you can in theory set on is number of current bits that are off, and you also don't want to make more than k operations. So that's what you do here. And then you just see like bit frequency is have many numbers in have this bit set, you shift it to the correct location and you add it to it. And at the very end, you want to take modulo. This is just what it is. In Python, I made use of sum function here. Otherwise, it's the same. So yeah, more or less the same thing. And I don't. Here I did a terrible thing. I cast it to int60. In general, like casting like this is terrible. Don't do that, please. I won't explain reasons now because it's not a C++ training, but just don't do this if you can. Okay, another problem, unique numbers from sublist bitwise ORs. Oh, this is actually kind of strange problem where my Python solution works faster than my C++ solution. And my is like, what? How can Python work faster than C++? I think it's because like I did something terribly wrong in C++, but I'm not sure. So we'll cover like this solution first. So we want to find out how many, like for every sublist is a continuous subsegment. We want to find what is bitwise OR of these numbers. And then we want to count like how many different values can be obtained in such manner. One way to do it is to notice that whenever you are in some location, like I'll compute like what are all possible values that end here. I have last index. So we have some prefix and I want to find out how many different values there are of this kind. So from I to some, from R to some L. So suffixes of a prefix. And the reason why I want to compute this is because it's easier than to recompute when I add a new number. Interesting observation. Suppose here we have 1. If we here have another one, I just can ignore it. I'm interested in different values. So suppose here we have 2. And then OR will be 3. If the OR of this is again 3, I ignore it. Otherwise, it's at least 7. So more and more bits have to be turned on to get a new value of OR. And in fact, we can have at most 30 different values of OR because we have to turn on another bit all the time and we don't have all that many bits. So at any point in the program, like there are at most 30 different values of OR on suffixes of our prefix. So this set always has at most 30 elements, and you just compute, you add a new number, you compute all ORs, you again take a set and add 0. The 0 is necessary because it represents like empty sublist, but for some reasons, empty sublist is not considered a valid sublist. So if there's no 0 in num, then we have to subtract 1. Whatever. So you kind of do the brute force, but because you made an observation that there are not many numbers in that set, it means that everything works in like n log max, right? By log max, I denote like take maximum number from nums and we take its log, its number of set bits. So it's something like 30n. I'm not sure if it's possible to do it like in true linear time, but something like this works. I found it interesting because often you may think like your bitwise manipulations are too slow, but they're not, because like it's hard to get many different values of OR that are chained, in the meaning that each next includes all set bits of the previous. And also it's not possible to get like too many different values of AND that are chained, of bitwise AND. And basically, AND OR game from earlier video today makes use of exactly that concept. So I found it very interesting that I ran like in 2 problems very recently that you make use of the same idea. So that's why I wanted to share it with you. Now we are getting into somewhat more advanced problems. I will cover this one first because that one is a bit harder. Here we have 2 numbers A and B, and we want to make their bitwise OR equal to target in a minimum number of flips of bits in A and B. The way to do it, you iterate over bits at the same time. So you take the current bit of first number, of second, of target, and then you just see what like optimal updates are bit independent. So for every bit, you want to minimize number of updates separated. If current bit in target is set, and the only way when we need to change something is when all bits, both bits in first and second are off. In this case, we want to change one of them, and we'll have one more update. Otherwise, if target bit is not set, if both bits in arguments are set, then we have to turn them off both. If one of them is set, then we want to turn one bit off. And if both are off, then bitwise OR is already 0 in this bit. So yeah, like some manipulation like this are possible. Also in Python, you can define a function, something like cost. What is the cost for 3 bits, and then just sum it over all bits. I found it interesting. Some function has many different uses in Python. So that's why I wanted to share. Again, interesting problem. We want to compute bitwise AND of all numbers in some range. Now the way I do it here is like, I think, suppose that now we have number, or sorry. Suppose that now we have number like this. While we add bits here, like bitwise AND does not really change because these were already off in start. So this is why I'm not interested in like changing these bits. I jump straight away to changing these bits and getting this, because it's when the bitwise AND can change, because it's first time it decreases. So I jump straight away to this situation. And if this number, if like this number to what I jumped is still in range, then I take bitwise AND, and then I will make another jump. Sometimes I can make jumps like this. So I turn a consecutive segment of ones, because when we add one here, it carries over. And the reason why it works fast, because like this works, what I currently implemented works in this time. You can get rid of log of the square of log, but we have at most that many jumps, and each jump takes at most that much time, because you have to find what is the lowest bit that is turned on. However, my solution in C++, I believe. Yeah, we can again make use of built-in count tail in zeros to find what is the lowest set bit immediately in like constant time. So this works in true logarithmic time. I found it interesting. Actually, let's see whether some. Oh, it's interesting. but I don't know. I don't know. We can find the part in the start. Okay. Okay, so there are no solutions like mine. I should post it like in a tutorial. I found it more like natural, because you kind of do what you're told, you just skip in numbers that can't change the OR. Whether in like recursive solutions or while loop, while getting rid of bits, it just, you have to make some observations. And here observation is rather simpler. It's like skip whatever does not change bitwise. Again, because of some chain property. So range squares, we have an array of numbers. We want to quickly answer what is XOR from I to J. Here, important property of XOR comes into play is that if you have A XOR A, then it's 0. Particularly if you have like A XOR B XOR A, then it's B. Because you can obviously commutate arguments of the XOR. So because of that, the problem is the same as find sum of the range quickly. And finding sum is done with prefix sums. Finding XOR is done with prefix XORs. Like you take whatever is from nums 0 to nums j, and then you get rid of nums 0 to nums I minus 1 by XORing with them again. So when you XOR with one number twice, it's the same as not XORing at all. This is why you can make use of prefix XORs. Another important concept. Same thing happens in C++, with the exception of, for whatever reason, I wanted to do it like that, so I use reserve. I don't know why. Oh, another kind of cool concept is gray codes. It's a way to iterate over numbers from 0 to something like 2 to the power of n minus 1, changing 1 bit at a time. So it starts with something like 0, 1. Here only 1 bit changes. Actually, I should. So it changes like this, right? Starts like this. And then what we do is we change second bit, then we turn off first bit, then we turn on third bit, then we turn on first bit, then we turn off this bit, then we turn off this bit. So for every pair of adjacent elements in the order, so we start like this, we continue like this, only 1 bit changes. It's a very efficient way to loop over all bit masks, I guess. But it's usually used for some smart tricks. For example, in CodeChef General Challenge, we had a problem which was like tile. I can't. So these two letters are different. I hope you agree. It was tile squares. I should write Q just like this. And there you had to make use of gray codes because you had like a board of cells, they had diagonals in them. You was able to ask question and then diagonal flips. And because like you wanted to iterate over all possible states of 2x2 square in minimum number of questions possible, that's why you wanted to grade codes to change one bit at a time, not to spend like 4 questions to get from one state to another. If you iterate in order, like from you can already see that here we made 2 changes. Whereas here we had like smaller number of changes. I think on average, if you iterate in this order, we make log n changes, log n over 2. And here we have like 1. So it's better if you want to iterate over all possible numbers in this range in like with 1 change per iteration. And this problem is more or less about that. It's hard because it's hard to notice the pattern, but implementation is rather straightforward. It just reverses the gray codes. So we had some legend here. It translates into human language as compute inverse gray code. And this is the way to do it. And we have only one problem left. It's max XOR of 2 integers. We want to find max XOR of 2 numbers in the array. One possible way to do it is to make use of a bit try, which is obviously not in Python written here. Yeah, I wanted to translate solution to Python, but I'm not all that good in object-oriented programming in Python, and I really wanted to make use of classes here. So yeah, I have a class bit_try. It can insert numbers. Capital N is the number of bits in numbers that you want to insert. And it can find maximum XOR with whatever number you give it to it. Now, try overall and bit_try are important topics. At least, yeah, I faced several problems concerned with such operations, like lately. It is kind of quick to type if you don't use class, if you don't use unique pointers, obviously. You don't want to write like that in the context. But actually, like I tested this implementation on several different problems, and it was kind of quick. So it was not slow or anything like that. So it may be like not 60 milliseconds, but 180 milliseconds, but it's still usually enough to pass. Something like this. And the way to do it, to find maximum XOR is you want to go to the opposite branch because it maximizes XOR. If you can go to the opposite branch, then you can. If you can't, then you go to whatever branch you can go to. And if you can't go anywhere, then something went wrong and there's no such XOR. That's what we do. We just insert all numbers into try in the beginning, and then for every number we find max XOR in try. And it works in n log max time. Log max is sort of short. So again, not particularly fast solution. I'm not sure whether it's actually there may be some. It's the same thing. Like Salvo does not have library implementation for try because it's kind of necessary. It's quick to type. You can always type it on the contest itself. Yeah, well, here we have better implementation. Here we have try not, try. This is the way you want to do it in Python. Oh, okay. Okay. So yeah, try and bit try is another important topic in terms of bit manipulations. And that's pretty much it for today. I mean, we covered 15 problems, 14. Is it 14 or 15? I'm not sure. And I would like you to get at least several ideas from here. I mean, so what ideas we had? You can check whether number is odd. You can check whether or not is bit is set. What else can you do? You can discard last bit. You can make use of built-ins. Most useful ones are pop count, count leading zeros, count tailing zeros. You can have bit try. You can use XOR properties to get rid of several of like multiple occurrences of one number. You can have prefix XORs. You can also have things like bit frequency. And so how many times in an array some bit is set. Maybe I've already forgot about some concept, but I think like this 8 or so concepts solve most of the questions of interview style questions. On Codeforces, you sometimes have to think a bit more, and you also have to make use of bit masks for some brute force solutions. You can also have like DP on bit masks. But these are somewhat, okay, this is not advanced topic. This is not very advanced topic. And also you have DP on bit sets. I believe in this general charge called chef, I solved, there are two problems that are DP on bit sets, and I was a bit surprised by it. Because after I solved the first one that was about DP on bit sets, and I seen the second one, I thought like, no, it can't be the same thing again, but it turned out to be the same thing. So kind of unfortunately, having two problems on the same ID in one contest, I don't know, man. But anyways, I mean, it was good to have some problems. So that's pretty much it. I wanted to talk about bit manipulations. It's kind of introductory thing, but we also have some more advanced topics. I would not say like they are Div1, they are at most, like most of the concepts are perfectly fine for Div3. Some concepts are more like Div2, but again, low Div2, so it's like 1900. After 1900, you should know all of this stuff, just because it's not difficult and it sometimes helps. So that's it for today. What can I say? What can I say? Thanks for watching. Hope you enjoyed. Hope all of these videos help you guys. to get better at competitive programming, at interviews, things like that. I definitely find some new things when solving such problems, and I also should fix my light setup. But whatever, it's for another video. So yeah, thanks for watching. See you in the next one. Bye bye.